For our project, we wanted to create a kinetic sculpture depicting a flower garden in motion. Our design consists of a flower, butterfly, and sun, all operated by a DC motor that drives pulleys, linkages, and cams that allow for their movement. We are Team MCEC, and my name is Danielle Burke.
Hello, I'm Amy Ta, and I am the test engineer.
I'm Alex Kelling, the manufacturing engineer.
I'm Nolan Bruner, systems engineer.
This is Yu, I'm the CAD engineer in this project. In the slide, there is the picture of the previous iteration design. In the design, it was difficult to time the opening and closing of the wings and pedals, such that they did not collide. So we placed them both on a single shaft with different shaped cams to add in the components rise and fall at an alternating rate. The butterfly's wings were initially designed to be supported by U-bolts, which was screwed into the top plates of the box. But aesthetically, this left much to be desired. To address this, we instead opted to secure the wings by inserting rods into the back plate. That wings called the restaurant wedge resulted in a far sleeker design for support. To ensure the components outside the box were actually secured, we also added a standoff bracket to the top plate of the final model.
Before reaching the final version of our project, the design went through a few iterations. The model shown on the left was the first iteration we designed in CAD after sketching out ideas for this garden. After creating our first model of the flower garden, we realized that there were going to be problems with the interference of the butterfly and flower components with them situated on their own rods, controlled by gears. To fix this, we changed their orientation to be inline on a single camshaft and controlled by a pulley system attached to the drive shaft. We had also planned for the box and components to be made out of acrylic and be laser cut, but changed our design to utilize water-jetted aluminum for a stronger box. The biggest obstacle we faced before achieving our final model was that the machines at the Idea Forge went down before we actually went into the manufacturing phase. This meant that the entire box, sun, and linkage system, along with the butterfly that were meant to be water-jetted parts, needed to be redesigned as laser-cut parts instead. So we ended up using MDF for those pieces. The cams, butterfly, and flower, as well as their supporting mechanisms, were all 3D printed rather than machined due to this complication. Since things were being laser-cut now instead of water-jetted, we decided to just glue the box together since the box didn't withstand too much movement and doesn't need industrial-grade supports to keep it in place. However, despite these challenges in our design process, we ultimately were able to create a working flower garden that moved in the way that we wanted.
Our design seeks to capture the essence of better days in a world before COVID-19, when everything seemed to be a little bit brighter and happier. Our kinetic sculpture captures a flower garden in motion, a blossoming flower accompanied by a fluttering butterfly under the rising and setting sun. Our 12-volt DC motor is powered by A23 batteries. We extended the motor shaft by coupling the shaft with a shorter D-profile shaft. With the layout of our animated elements, we decided to direct drive the sun linkage system and then connect the motor to the camshaft via a pulley system. As a butterfly naturally flutters at a faster rate than the rate at which a flower blooms, we wanted to achieve those different speeds. However, as the butterfly and flower are driven by the same shaft, we had to find a way to manipulate the vertical velocity of the movements using the same angular velocity of the shaft. We ended up altering the profiles of the cams to achieve different revolutions on the vertical movements of the two cam systems relative to one another. To speed up the fluttering of the butterfly, we added two rounded vertices, creating a triangular profile. The sun linkage system relies on the direct drive of the motor. At the end of the motor shaft, we added a circular cam to connect the linkages to the motor's angular velocity. The long linkage is pinned at one end and supporting the sun on the other. We purposely off-centered the short linkage on the cam and lowered its connection with the long arm to create an arc movement for the sun. The only machining we ended up doing was cutting down a single D-shaft into the two you see in our drivetrain. The entire box encasing our drivetrain, the linkages, and sun were all laser cut from an MDF board. We had 3D printed the butterfly, flower pipe, and cams. A few of the 3D printed parts, as you can see, had excess materials that had to be disposed of before assembly. The flower petals had also been printed with incorrectly sized holes and hinges, so they had to be drilled and sanded down to fit with the flower connector. The only other issue that came up during assembly pertained to the linkage system. Initially, the linkages were to be threaded so that they could be screwed together without nuts. As we switched to laser cutting them instead, we had to resort to screws that were able to self-thread through the linkages and circular cam. Our sum was also originally designed to be secured with a countersunk screw. Similarly, the switch to laser cutting resulted in the screw not fitting. We found a longer screw that could secure the sun and spacer with additional nuts. The only thing we were not so prepared for was the effect of the weight of the sun relative to the long linkage. The clearance we allotted for ended up being a tad too small to account for the leaning of the linkage into the backboard due to the sun's weight. Improvising, we created our own spacer out of cardboard and painted one side to reduce friction. Attaching it to the long linkage, we were able to clear the nuts in the back.
The first critical component of our design is the camshaft. We chose this as a critical component because it drives 2 out of the 3 moving parts on our project, so we thought it was a pretty important piece. We chose a 1/4 inch diameter shaft because it was easy to find bushings and pulleys to fit on it, and we thought that that would be strong enough to support the small loads that it is subjected to. So a quick overview of what it looks like. It's supported on either end by bushings, when it's constrained axially by the blocks that forms the structure of our project. It is driven by a pulley from the main drive shaft, and it outputs power at the 2 cams. One goes to the butterfly, the other to the flower. To analyze this, we look at the bending moment and the weight exerted by the butterfly and the flower and the torque exerted by the pulley and cams. So all of this analysis is going to be static. That is, we're going to analyze it as a beam with vertical point loads, and we'll use the maximum amount of torque exerted by the cams because it isn't exactly a constant amount, and it's actually pretty tricky to derive time-dependent equations for the force that they exert. We find the maximum bending moment at the butterfly cam, which also happens to be where torque through the shaft is maximized. So that's where we're going to be most prone to failure. Using our bending moment equation, sigma bend is equal to 5,940 psi, and using the torsion equation, tau is equal to 56 psi. Using our von Mises equivalent stress equation, equivalent stress is 5,941 psi. Torque isn't really a factor, but it's important to always check. According to McMaster Carr, the yield strength of our camshaft is 60,000 psi, giving us a safety factor of 10.1. This is great news since we approximated a D-shaped shaft as round, and we didn't account for fatigue failure, both of which, had we accounted for them, could decrease our safety factor, but luckily we have some wiggle room. So we shouldn't need to worry about failure of our project, especially in the foreseeable runtime.
For critical component number 2, we analyzed the screws that attach our mounted sleeve bearing to the wall. The mounted sleeve bearing ensures our shaft was axially and spatially constrained. This part is a critical component as it ensures that our cams and pulley on our shaft are aligned, ensuring proper operation of our whole machine. To analyze this part, we treated the 256 by 1/2 inch 18-8 stainless steel screw as a rod, fixed at one end with the wall and fixed at the other end with a nut. A combined loading analysis is used in which both bending from the cams and twisting from the mounted bearings are applied. The distortional energy theorem is utilized to analyze for failure. With a force of 0.15 pounds per screw, we analyze the stress experienced in the screws. Since the screw length to depth ratio is not 10:1, we cannot neglect transverse shear stress. Finding the von Mises stress equivalent at points A and B on the screw, we find that the stress in the screw is significantly less than the yield strength of the material. We can reasonably assume that these parts would not fail due to normal loading. The stainless steel screws would probably be one of the last points of failure in our model, which is made of mostly 3D printed or MDF parts. Although not likely to fail, these parts are still critical to our model, and ensuring their function is important to ensure our engineering safety of our project.